Hello everyone, I'm Qilong Liu and I'm a PhD student in the Technology University of Eindhoven, and I'm specialized in the wideband data converter clusters in the IC group. And today I will give a short introduction about my research topic, which is a wideband continuous time Sigma-Delta ADCs. What will be the final limit, power limit to achieve a high wideband and a high linearity at the same time? In the Nyquist ADCs, usually we have a simple quantizer which trying to quantize analog signals with a very finer step. And from that, we can get the output, which is digital bits. And in the Sigma-Delta ADCs, it goes to the same fashion, but we can utilize a coarse quantizer compared to a Nyquist ADC. Because in the Nyquist ADCs, we can have a loop filter in front of any quantizer. And the loop filters will have a certain gain for the in-band side. So it will forms like this system. The input signal will go into the loop filter with the feedback, negative feedback, and output will be final digitized signal. So in this case, in the end, we can find all the coarse quantization inject at these nodes will be suppressed after referring back to the input side due to the high gain of the loop filter. And in the spectrums, the quantization noise will also behave differently. For the Nyquist ADCs, the noise will be spread uniformly between 0 to Fs. However, in the oversampled system, a Sigma-Delta ADC, the noise is not uniformly distributed, actually is shaped. So in the end, the noise will behave in this fashion. This is Fs. So even though we have different type of noise shaping, then the comparison should be made by comparing all the auxiliary blocks that we need to use. And I will list them here. For example, the power of the driver and also the power of the anti-aliasing filter, linearity requirement, and also the digital signal processing unit after the ADC. So usually in the Nyquist ADCs, before any quantizer, we need a sample and hold block, which trying to convert the continuous time signal into discrete time, and then it will be processed by the clock, the ADC system. In this case, the current injected into this capacitor is not a very smooth behavior. For example, if we draw a time domain current versus versus time, so we can see when the switch goes on, we have a large current spike at the beginning, and then this current will settle to a certain value according to the accuracy requirement of the whole system. Usually in the ADC, only half of the time, or a proportion of the sampling time will be utilized. So in the end, only maybe half of the time should be used to achieve a certain accuracy. And in this case, we can see the current flowing to this switch occurs along a high wide range. For example, from a high current range here to a very small current. And all the current should be delivered by the buffer before it. If we design it in the class A mode, then the biasing current of the Nyquist ADC should goes to a very wide range, and this one gives the final bottleneck of the power of the whole system. If we go back to the continuous time Sigma-Delta ADCs, the input is not a sample and hold, but a purely simple impedance, for example, a resistor. So all the current flowing to this ADC will be quite static. It will only behave very smoothly from 0 to the clock frequency Ts. So this will be the final current delivered by the buffer to drive the whole ADC. And if you compare the power of this one and this one, you can see a lot of benefit by using continuous time data converters. And second, I will talk about the anti-aliasing filter in both systems. Usually in the communication scenarios, not only the signal itself, but we also have a lot of interference from outside of the signal frequency. For example, this is the signal we want to quantize. However, we also have a very strong signal somewhere here, which we're trying to get rid of it. In order to do it, we have to introduce an anti-aliasing filter before going to any sampled system, which means all the unwanted signal should be filtered sharply before going to the ADC itself. And the design of such filter is not a simple thing. However, if you go to a continuous time Sigma-Delta ADCs, you can surprisingly find that this anti-aliasing filter has been integrated as the loop filter inside the whole system. So by compare the blocks we are trying to design, in the end, we can have simplified the anti-aliasing filter side as the overall baseband system. And next, I will talk about the linearity of the traditional Nyquist ADC and the continuous time Sigma-Delta. So here are the several basic types of the Nyquist ADCs. And for the flash ADC, usually we are limited by the offset of different comparators. It will limit the final INL and will also degrade the linearity. For the SAR ADCs, we are suffered from the binary scale, the D2A converter, which gives a very huge jump in the middle transition, which also limited the linearity, and also the dynamic offset of SAR ADC in a high accuracy system. In the pipeline ADCs, we can get rid of the binary scale, the D2A, by using univariate cells. However, for the interstage gains, we are suffer from the gain error and the memory effect. Both of them will also be translated as the INL in the transfer curve, and that also limited the linearity. In the time-interleaved system, we can design multiple channels which are multiplexed by high-frequency drivers. And for each channel, it can be composed of any of them or a hybrid of all of them. In the time-interleaved ADCs, we are suffer even more things. For example, the offset between different channels, the gain errors, and also the sampling skews between different channels. So in the end, the linearity will be not as good as a single one. If you go back to the continuous time ADCs, you can see, surprisingly found, there's only one block which is critical for the linearity, which is the D2A on this side. Because in this case, we don't have any gain before this block. All the errors introduced here will be referred back as the real unexpected errors. As long as we can design it as good as possible, we can get rid of the linearity problems. And since we can design it in the univariate form as a D2A converters, so the offset, so the INL and DNL problem will be relaxed a lot. And the last, I will talk about the digital signal processing unit, which is after the ADCs. And here we can show some downside of the continuous time Sigma-Delta ADCs. Because usually in the signal Nyquist ADCs, we can just filter the noise out of band easily. But for the continuous time system, we have to extend the FS to a higher frequency in order to achieve similar in-band noise performance. Because we are using a coarse ADC, to achieve similar noise performance, we have to increase the clock frequency. And the increase of the clock frequency in the quantizer also means we have to design the digital backend in the higher frequency, which will cause the extra burden for the overall system. To really get rid of it, we are trying to design an oversampling system which can be used in a lower sampling frequency with respect to the signal bandwidth. So to recap, by comparing these two, we can save the power of the driver of the ADCs. We can get rid of the anti-aliasing filters. We can achieve a very nice linearity by using simplified D2A side, and also trying to come up with good ideas, trying to reduce the clock frequency. In the end, we can achieve a better power and a high linearity by using continuous time Sigma-Delta. And that's to recap, by taking all the items into account, we can save the driver powers from the continuous time Sigma-Delta, and also throw away the anti-aliasing filters by reduce the design burden, and also relax the linearity requirement by simplify the D2A side converters, and also trying to design a low ISR system, trying to have a simplified digital signal processing unit. We're trying to achieve that the continuous time sigma delta will achieve a lower power compared to the Nyquist ADC as a whole system.